We will continue with the review of probability. Maybe I will take 2 more classes. So last time we did discrete random variable. Now today we will do continuous random variable. So continuous random variable. So as I said in previous classes, continuous random variable, we will define it when the CDF of the random variable is continuous, right? So a random variable x is with CDF fxx is said to be continuous if fxx is a continuous function, okay? Is a continuous function, obviously of x for all x in R. Discrete was when the range of the random variable was countable, but in the continuous case we say look at the CDF, and if CDF is a continuous function, then we call it a continuous. So the CDF could be like this, okay? So it is continuous. So it's essentially for the uniform, but we will come to that. So then we can define an equivalent of PMF, which is PDF, okay, in the continuous case. So the way, as I said, in discrete the pointwise probability values make sense, but in continuous it doesn't make sense. So we will define something equivalent of that by saying maybe the rate of change of fx, okay? So that will give us like the pointwise equivalent, okay? That's not exactly the same, but yeah, in this case it will be the rate of change, okay? So to do that, what we can do is we can start with, we can define it in a way that fxx, the PDF, okay, which is equivalent of PMF, as a rate of change of the probability value, okay? So this is like limit delta tends to 0, probability that x less than x plus delta, okay, and then divided by the delta, okay? So delta is the increment in x. So in the continuous case we define it in that way, the instantaneous change in the probability values at a point x, okay? So if we do some further calculations, then what we know is that this probability value can be given via CDF, because CDF is the probability value cumulative until x. In this case we are saying between this and this. So for this interval it will be until here minus until here, okay? So I can write this probability value in terms of CDF. So probability that x less than x plus delta, it could be written as fx x plus delta, all probability until x plus delta, minus all probability until x. So we can write this as fx x plus delta minus fx x, okay? So way I am going towards is that I want to show that fxx is a differentiation of the cumulative. So if I substitute this, it seems to be the case, right? So if we call this n star, so star becomes, so fxx is now, we put this in the numerator, so limit delta tends to 0 plus fx x plus delta minus fxx by delta. Now this is exactly the meaning of derivative of fx function, right? So this is nothing but the derivative of fx at x, okay? So in other words, the PDF function that we want to define, which is an equivalent of the PMF in the discrete case, can be obtained via differentiation of the CDF, okay? So we note this down. So we can define the PDF like that, okay? So definition PDF, okay? So consider continuous random variable. So I keep using this notation, right? Continuous CONT random var. Okay, so I hope you can make from the context random variable x with CDF fxx. Then the function which is the PDF is defined as then fxx, which is defined as d by dx of capital F fx. And obviously fx has to be differentiable, so we assume that fx is differentiable. Okay, at x is called a PDF, is called probability density function, is called BILIT, probability density function, or PDF in short. Okay, not the PDF file, okay, portable document format, but it's probability density function. Okay, so idea here is that in continuous case you don't have pointwise values, that doesn't make sense, so define something which is rate of change. Okay, that acts like a pointwise equivalent. Okay, not exactly the same maybe, but equivalent form. Okay, so so I can define yeah, before defining any distribution, let me write down the properties of the PDF. Okay, so just like in the discrete case, the sum of the PMF was 1 and so on, right? Here also we will have the equivalent. In place of sum in the continuous case, we have integral, right? So basically wherever we have sum, it will be integral now. Okay, that's the major difference. So let us write down the properties. So properties of PDF and CDF. Okay, so properties of PDF and CDF. So just like PMF values, which were probability values, were non-negative, here also we say it's non-negative. Okay, because of the fact it is going to be non-negative because this guy is something positive and this guy is also positive, ratio of that, so it's going to be positive as well. So fx x is greater than equal to 0 for all x in R. Okay, and just like the PMF values, if I sum over all the probability, then it must be 1, right? So that's the axiom 3 of probability of a sample space, right? So in this case it will be integral, so minus infinity to infinity fx u du is 1, and it doesn't matter, you can take xx also or u also, it's fine, it's just a variable here. And if you want to compute the probability in a range, in an interval, then a less than x less than equal to b is fx b minus fx a, which in the form of integral, it will be integral from a to b, right? So this will be integral a to b, and this is integral of fx u du. Okay, and more generally, if you want to compute these probability values over a set, then more generally for set A, if you have to compute probability that x is in A, then it will be a fx u du. Okay, so basically you integrate over the whatever the set you are supposed to calculate the probability on, you just have to put those values. So let us do a quick example of a continuous PDF. By the way, this class will go for 3 hours, but there will be a splitting to make up for the previous class. So if you want, you can leave, but the videos will be there. Okay. So I will continue this for 3 hours. I will split this into 2. Okay. So let us see an example. Okay. So if you can sit for a movie, then also it's fine, right? Think of this like a 3-hour, right? It may not be interesting one, but okay. fxx is c e to the minus x, x greater than equal to 0, 0 otherwise. Okay, and what are we supposed to find? Okay, we are supposed to find constant c, and to find a constant c we use the property that integral of any PDF must be 1. So we integrate and equal to 1, from there we should get the c. Okay, so let us write down. So find c. B is find CDF of x, which is fxx. Okay, so then next question is give us the value of the CDF. Okay, so and the third question is find the probability within certain range. Okay, so C is find probability that 1 less than x less than 3. Okay, so let us do this one by one. So the first one is easy. So using property 2, okay, so using property 2, integral of this guy, so it's only valid for non-zero for greater than or equal to 0. So my lower limit will be 0 to infinity. Okay, so 0 to infinity. I can start from minus infinity, but minus infinity to 0 is anyway 0, right? So c e to the minus x dx must be 1. So then it's about recalling your calculus. So integral of e to the minus x is minus e to the minus x. Okay, so this is c comes out e to the minus x by minus 1 basically. So this is 0 to infinity minus c. Now infinity is 0 and 0 it's 1, right? So at infinity e to the minus infinity minus e to the minus 0, right? Minus 0 is 0. So this is minus c is 1, right? It's minus 1. Okay, and so this becomes plus c, and all this was supposed to be 1. So this implies c is 1. Okay, so we can now we have the PDF now. Okay, then we can maybe find the CDF using the PDF. Now CDF is a cumulative until certain x. So it's like integral of PDF minus infinity until x. Okay, so the CDF can be found at any given point x. So B is fxx is minus infinity, so cumulative until x, and we substitute the PDF value. So c is now 1 is e to the minus x. So e to the minus x. But then here again minus infinity to 0, it's anyway 0, right? So we can indeed make it 0 to x, e to the minus x dx, e to the minus x, and then 0 to 2x. Okay, so minus came out, and then it's like e to the minus x. So 1 minus 1. So 1 minus e to the minus x. Right. So and then c is probability values between 1 and 3. So integral becomes 1 to 3 of the PDF. Okay, so this is from the property 3. In the continuous case, equality and no equality doesn't make sense, because in continuous case a less than x less than equal to b is same as a less than x less than b, or a less than equal to x less than b, all are same. In continuous case it doesn't matter, but in discrete case it will matter, because there may be a jump right at the b, and until b it's not a jump, right? So that in the discrete case we have to be careful about less or less equal, right? Okay, so here probability that 1 less than x less than 3 is 1 to 3, and then we put e to the minus x dx. Okay, so I'm not even going to do this. Okay, so you do these simple things, right? Now we can define expectations and variance in the continuous case as well. So let us do that. So it's a very simple, like summation changes to integral. Okay, so for a continuous case, expectation of a random variable x continuous, then this is equal to minus to infinity x fxx dx. Okay, so what is different is we have PDF here in place of PMF, and here we have integral in place of the sum. Okay, that's the only difference. So as an exercise, so you can try that let us say x follows uniform, and I will define uniform right now. So uniform distribution is given by fxx is 1 by b minus a less than x less than b, and 0 x less than a or x greater than b. Okay, so this is the uniform distribution defined now, and given the PDF is given to you, now you're supposed to find the expectation, okay, of the x which is uniform within AB. Okay, so obviously the integral will boil down to AB because outside it's 0 anyway, so it will be integral AB of this guy. Okay, so that is something you are supposed to do. Okay, so I leave this as an exercise. Okay, so now we can also have expectation of function of a random variable, which we also did in the discrete case. So it's extension of that. So expected value of function of continuous random variable. Okay, so so it's the same. It's just the integral will be there now. So if I want to compute expectation of a function of a random variable, then this will be integral of gx, and but then the PDF is of the x. Okay, so this is fx x dx. Okay, and this is over the range of x. I mean, expectation will be minus infinity. If x gives me certain range like this, that will collapse to that range, but by definition you are supposed to integrate from minus infinity to infinity. Okay, you just put the gx, but then the PDF should be of the x. Okay, and the linearity and all this holds here also. It's same thing. Variance also is same. In fact, the variance formula is exactly the same, but inside variance expectations is there, and for continuous they are supposed to be integrals, right? So variance formula is exactly same. It's just that calculation of expectation is different, right? Because it involves integrals. Okay. Okay. Let us see how we can compute PDF and CDF of a function of a of some random variable. Okay. In fact, this is one of the main things. Okay. In this course, you will see we will transform one random variable to another. Okay, and we want to know how the PDF distribution changes from distribution is given by the PDF. Okay, so how distribution of x, if I apply a function, then how the distribution changes. So what is the PDF of the transform random variable, right? So let us see one example of x is uniform 0 1 random variable, and y is e to the x. So x PDF you are given, and then you are supposed to find PDF of y, which is e to the x. Okay, so let us try to work out this. Later we will also write down a method of transform. Okay, and that is a more generic way to do transformations. Okay, but here we can do away without the method of transform. Okay, so the CDF, because this is a uniform, the CDF of x is given by, so CDF of x is given by fxx. So you can verify this, why the CDF of uniform will be like what I'm writing. Okay, so you can verify this as a separate thing, because PDF, you do the integral and minus infinity to x, and then you get the CDF values. So this is 0 for x less than 0. This is x for 0 less than x less than equal to 1, and this is 1 for x greater than 1. Okay, so in this case the range of x is clear. It's 0 1, right? So range of x, but when finding a PDF, one of the first thing you should do is the range of in this case the range of y also. Okay, so if x is between 0 and 1, what is the range of y? So first let us write down range of x, which is 0 1, and range of y will be, it's an increasing function, right? So 0 to e, right? I mean 1 to e, I guess, right? So 1 to e 1 to E, right? So let us try to find out these. So basically, you're supposed to find the PDF values for these values of y. You're supposed to provide a function for these ranges of the y values, okay? The probability values or the CDF values, okay? Okay, so let us see Fy y, which is cumulative until y less than equal to y. And what happens if it's y is less than 1? Obviously, since range of y is, that's why writing range is important. So range of y, so for y less than 1, certainly it's a 0, okay? So there is nothing until y less than 1, okay? That's found by range itself, okay? So this is 0 when y is less than 1. And it is also okay because CDF must cumulative at some point onwards beyond the range, it must be 1 because of the third axiom of probability. By the end point of the range, it must accumulate all the probability values. So E onwards, the CDF must remain 1, okay, like flat, right? So Fyy is probability that y less than equal to y will be 1 for y greater than equal to E. Okay, so that's immediately, like, boundary cases are immediately handled looking at the range. The main part now left is the interval 1 to E. Okay, so let us write down, we will use the definition itself. So Fy is a cumulative probability P of y less than y, but y is e to the x, so e to the x is less than y, solve for x, and we go back to the x. The whole idea is write the definition. So y less than equal to y, but y is e to the x, e to x less than equal to y, so solve for x. Then you change your, go back to the base, you go back to the base probability PDF and then use that. Okay, that's the main idea. So now in general, for the range of values between 1 and E, I have probability y less than equal to y. Now substitute y is e to the x less than equal to y, and solve for x. So I take a log, then probability of x less than equal to ln y. So it's equal to probability of x less than equal to ln y. And now you see, it is a problem on x now. Okay, so I'm allowed to use a CDF of x. Okay, so CDF of x I can use, which is listed here. And this is, yeah, for ln y, so x lying between x up to ln y, right? Now it also depends on what ln y is, right? So I have to figure out where it is, right? For y in 1 and E, right? So ln y, log of 1 is ln log is 0, right? It's natural, and then E is 1. So it seems like it fits directly in this case. So ln y lies between 0 and 1, right? So from there it seems like it will be x, which in our case is like ln y. Okay, so we will just note this down. So this is basically fx of ln y. Okay, and this is fx of ln y because ln y greater than equal to 0, this indeed lies between the range, and this is because y lies between 1 and E. Okay, or 1 less than equal to y less than E. Okay, so all this happening because of that. And so this then in that case is just spits out x, right? So this is like ln y. Okay, so we have covered because we're supposed to find only for 1 and E, and less than 1 is covered, greater than E is covered. So basically we have the CDF for the full case. So then we can write Fyy is 0 for y less than 1. We just like summarize this in one place. For y, 1 less than equal to y less than E, and then it's 0 for y greater than E. So this is how we were given one distribution, and then we did a transform, and then we could find the distribution of the transform variable. Okay, you can also take a differentiation and you can get a PDF also. So this guy is 0 0. Okay, and yeah, there is something like that. I mean, you don't have to take subgradient, although there is a corner or something. Okay, it takes care of that. We just take derivative of this, because there may be like ln y is like this, right? And it's like 0. So there must be a corner. Okay, but you ignore that. Okay, take 0 and then it's 1 over y and 0. Okay, so fx small fyy will be 0 1 by y 0. Okay, so you can figure this out because it's 0 here and here, so combine you can say otherwise. Okay, okay, so in this course we are interested in sampling a random variable from something known. So it could be uniform also. Okay, in fact uniform is the best possible case. Usually even if you ask from some normal or something, it will pick from uniform, it will do some transformations, and then it will give you something from the normal. So you will take something from uniform, and then you expect that it will give you some distribution Q, which is some interesting cat distribution. Okay, so I will use cat maybe 1,000 times in this course. Okay, I'm sorry for the cats, but this is what I mean. It could be anything, right? So whatever data you are working on, it could be faces. Okay, so most generative models, even when writing papers, we are like using a lot of images, right? So faces are good ones, because faces you can like judge, okay, is it really looking like face? But if you use some distributions of the bridges or something, sometimes the bridges are constructed but it looks broken. Okay, so that becomes a little bit hard, like it's creative or it's but faces you can say, okay, it's indeed look like face, right? So in this course what we are interested in is to go from known. Okay, here like we can sample basically. Okay, so I can sample from something uniform 0 1, so like everything is known here, and then go to something interesting, right? Something interesting Q, right? And there will be a model in the middle, right? This model will be trained over this, and then it will start what I want as a Q, right? So but this is an easier problem than the generative modeling problem, because this is easier because the problem is that here it's even I'm going from something deterministic, and this transformation is given to me, but generative modeling is more of an statistical problem. Okay, generative modeling is statistical problem because the model that I am going to train on, okay, to go from a given one to something else, that has to be statistically estimated. Okay, so by statistically estimated we mean we will look at a lot of samples, okay, on which to train, okay, and do some kind of likelihood estimates. Okay, so we will need estimations. Okay, not in this case like it's a direct function given to me and I apply this, and even method of transform is there, so I can do all those and solve and find a distribution after the transformation. So but in generative modeling, even these guys which are data based, okay, so a lot of cat images will be there. From there I will kind of estimate a, so what I want is cat distributions. I will estimate a distribution p hat, which which the underlying distribution is perhaps p. Okay, so my model will build something called p hat. Okay, and from there I will start generating samples which may look like a cat or so on. Okay, so we will come to that if it's not making too much sense. The statistical part will not make sense right now because we have not done that. So what I'm trying to say is this is easier, okay, well, but generative modeling is a little bit tricky because it's more of a statistical problem. Okay, it has to be estimated via that data. Underlying distribution is obviously not known. It has to be approximated basically. So that will, all this we will discuss in detail in after 2 classes. Okay, so you will see more intuition behind what I'm saying. Okay, so we have seen a simple transformation. In this case, we could do this, but then we can also have some generic formula to find distributions of a transform variable. So some of the older ideas of generative modeling are based on knowing how to do the transformations, okay, but with statistics included. Okay, so we will come to that in detail, but let us see what is a method of transform. So I can write down the formula without derivation because we don't have that much time. In a prob and stat course, I usually teach this in detail. So the method of transform so suppose x continuous random variable, g is a function from R to R, is for the moment let us assume that these transformations are monotonic and increasing, but then we can make it into a more generic transform that necessarily does not have to be increasing function. Okay, it can be increasing or decreasing and so on. We have to do some piecewise thing. Okay, but for the moment let us assume that these transformations we are using are strictly monotonic differentiable functions. Okay, so let that transform be g of y is g of x. Okay, then the method of transform says without deriving this. Okay, you can go ahead and look up the derivations and meet me personally if you want to, but I will write down the method of transform. So PDF will be found as fx x1 divided by g prime x1. So g prime is like the derivative of g, and then this is the mod, and this will be fx x1 dx1 by dy. Now I have to explain what is x1. So where gx1 is y, okay, so where gx1 is y and it is 0 otherwise, I mean not otherwise, but it's like if gx equal to y has no solutions. If gx equals to y does not have a solution. So basically you are supposed to solve an equation gx equals to y, find the solutions for that, and once you find that, then you plug into the PDF of x, because PDF of x is known, and furthermore you are supposed to do dx1 by dy, okay, or in other words dy by dx1, okay, and take the 1 over that, right? Okay. So let us see an example of that. From example it should be clear how to use this, and we will generalize this to 2 variable, okay, and then we will generalize this to vector of random variables. Okay, that's what will be useful for us. So let us go step by step. This is like R to R, so scalar to scalar transforms. Then we go from 2 variable transformations, xy goes to gxy, okay, and then we will make it into vector x1 x2 xn transform to g of x1 x2 xn. The generic formula will involve Jacobian and so on, okay. But okay, let us see the intuition with these simpler cases. So let us say we have an example, x continuous with PDF is given by fxx is 4x cube, 0 less than x less than equal to 1, and 0 otherwise. and the transformation that we are given is y is 1 over x, okay, and find PDF with y, PDF of y, okay. So remember that we said here is strictly monotonic, right? So monotonic means either strictly increasing or strictly decreasing, okay. So it includes both, but the function should not be strictly increasing at some within the domain and also decreasing, okay. It should have only one behavior, either strictly increasing or decreasing. That seems to be a special case, but we will generalize this later. But in this case, it's strictly increasing or decreasing in 0, 1, right? In 0, 1, or even like in general, right, in the domain, right? So x is taking positive values. So for those values, what is the value of y, right? 1 over x. It's increasing or decreasing? 0, 1, decreasing, right? So at 0, it's like just before 0, it's the maximum, infinity, and then gradually it comes down, right? So it's like this, right? As x goes to infinity, it's going to 0, right? So obviously, like, it doesn't cross, right? So it's asymptotic, right? So it's like gradually at infinity it will be 0, and this is 0, okay. So it is a strictly decreasing function, that's for sure, okay. So strictly decreasing, that is strictly monotonic. In this case, it's decreasing case. So okay, so one of these is satisfied. It is differentiable also, because 1 over x is differentiable in 0 onwards, so that's fine. And y is g of x, we know what is g of x now, 1 over x, and in that case we are supposed to get fy. We can substitute this, but then what is missing is x1, okay. But x1s are those for which g of x1 becomes y, okay. So we are supposed to find an x1 for which g of x1 is y. What is that x1? So what is that x1? 1 over y, okay. So x1 is 1 over y, right? So what is x1 for which g x1 is y? So x1 must be 1 over y, right? Then 1 over y, and then 1 over y becomes y, right? So solving g x1 is y, so g x1 is 1 over x1 is y. This implies x1 is 1 over y. So once we have x1, now we have to just substitute in place of x1 in the PDF of x, we have to substitute x1, which is 1 over y, and we have to take a derivative of x1 with y, okay. If we take a derivative of x1 with y, is minus 1 by y square, right? So d of x1 by dy is minus 1 over y squared, and so that's one ingredient we know. And fx x1 and the PDF is right there, right? So PDF is given to us. So let us write down the formula directly now. So fyy is yeah, maybe we can use this, okay. It's a little bit long, okay. So this is fyy. Okay, fyy is fx x1. So fx x1 is 4x1 cube. So let us first write down the formula itself. X1 divided by mod of g prime x1. I mean, we use the first one. I mean, we could have split, we could write further. So fx x1 is 4x1 cube. So let me do this, 4x1 cube. And I could use the first one, I could also the second one also, it doesn't matter, both are same. So dx1 by dy is minus 1 by y square, but I have to keep the mod, okay. There is something with the mod, but I'm not going there right now, okay. You just for the moment take it as a formula. Okay, in the decreasing case what happens? So negative negative happens and gets cancelled, so it's beneficial to keep the mod. Okay, so for the moment you leave that. So for whether it's a monotony increasing or decreasing, just keep the mod. Okay, so that fixes anything. Okay, so this is dx1 by dy, right, which is minus 1 by y squared, and x1 for us was 1 by y, right. So 4 1 by y cube times 1 by y squared, this is 4 by y 5, I hope. Yeah, so now we can now summarize everything in one place. So this is 4 by y to the 5, y greater than equal to 1 is 0 otherwise. Okay, so this is how we use the method of transform. Now let us go into a generic case where it's not just it's not necessarily monotonic. Okay, it's obviously any function will be monotonic in some segment, right? I mean, not any, but okay, there may be some special cases, but in general most functions will be monotonic in some interval increasing or in some interval decreasing or so on, right? So let us replace this now with a generic statement. So x continuous random variable, domain Rx, range is Rx, and y is Gx, the transform. And so in this case what we will do, we will partition the domain of x into finite number of intervals, right. So partition the range Rx into finite intervals such that Gx is monotonic, is strictly monotonic and differentiable in each partition. Then the PDF is given by fyy fx xi now and gxi, and then there will be a sum for each of the partition I equal 1 to n, and then I can also put a sum here. So I equal 1 to n fxi dxi by dy, and gxi is y. Okay, so this I denotes like whichever places you had xi for which we had y, you collect all those. Okay, and so basically these xi's are the solutions to gx equals to y, and you also sum over those only. Okay, so if the xi's are n of these solutions, then you are summing over those n. Okay, so that's a generic solution, generic transformation. Okay, so the example involves normal distribution, but I have not defined normal distribution. It is supposed to be defined later. Okay, I mean, anyway, let us do an example on this. The example involves normal distribution, but formally we will study, that's the most important distribution, right? So we will study that in detail anyway. But for the moment, let us assume that I don't even say it's normal. Okay, so it's some PDF, right? Okay, so let x continuous random variable, and fxx is 1 by square root of 2 pi, and e to the minus x square by 2 for all x in R, and let y equals to x square, find fyy. Okay, now x square, okay, x square on the positive side it increases, on the negative side it decreases. So it's a parabola. So certainly it belongs to this case. So we have to break this into two parts, less than 0, greater than 0, and then we have to solve for the gx equals to y. So basically we have to solve for the x. So if we solve for the x, we will get plus minus square root of y. Okay, so that so in that case we have y xi's are like x1 is plus square root of y, x2 is minus square root of y. Okay, and then individually we can take the dxi by dy. So square root of y by dy minus square root of y by dy, d by dy of that, and everything we have in place. Okay, so essentially this problem is is okay. So let us do this quickly. So here so gx equals to x square is strictly decreasing on, as I said, minus infinity to 0. Okay, now you could keep it open, and at 0 it's 0, right? Okay, and it is strictly increasing on 0 to plus infinity. So this gives us the two partition of that, and the solutions for this gx equals to y, the solutions of gx equals to y are given by, so gx equals to y, so x square is y, this implies x is plus minus square root of y. So x1 is, we can take it as, we keep the same notation, so let's say x1 is square root of y and x2 is minus square root of y. Okay, and that's it. So now we will use the formula now. So gx1 dx1 by dy also we need, right? So let us do dx1 by dy is, what is that? Minus 1 by 2 square root of y, right? Okay, so dx2 by dy is 1 by 2 square root of y, negatives should get cancelled. So we have the derivatives and everything is there. We just have to put in the formula. It's just that now we have to sum. There are x1 and x2, so we have to sum over those. So let us do that. Okay, so we have fyy is equal to fxx by, let us use the first, so g prime x1 plus this is 1 fx x2 by g prime x2, and we have to have the mod. Okay, now x1 is plus square root of y, so this is fx square root of y divided by, now g prime of x1, right? So it's here we have to write a dx1 by dy, which is and mod of that. So it's like in the denominator we have 2 square root of y, and then fx of minus square root of y by mod of minus 2 square root of y. Okay, so now we know fx, right? So we just have to substitute those in here, right? So this is 1 by 2 square root of y we can take out, right? 1 by 2 square root of y, yeah, 1 by 2 square root of y, and then fx we just substitute those values here. So we have e to the and then okay, 1 by 2 pi is also there, right? So basically 2 pi y could have gone there, both are square root, right? So 2 pi y and e to the square root of y, right? So e to the so square root of y becomes y, so minus y by 2 Okay, so both these guys have this common factor, and plus of e to the, now I have again it becomes y, so it becomes y eventually, right? Minus y by 2 and minus y by 2. Yeah, but then it's like 2 of those. Yeah, so half basically goes away, right? So plus again minus y by 2, right? So this is like 2, and 2 gets cancelled, and there was a 2 here also, right? Under the this was the 2 pi, right? So 2 pi is under square root, and then y was already there under square root. So this is 2 of these. So 2 gets cancelled. So it's like 1 by square root of 2 pi y e to the minus y by 2. Okay, and range of y is starting from 0 onwards, right? Because it's a square of x, right? So range of y is 0 to infinity. So that's how we saw that a function could be very generic. Still we can apply method of transform and get a distribution for the transform variable. It's just that we have to split them into intervals where it's monotonic, and solve for the root, the roots of the equation gx equals to y, and sum over that. Okay, so that's the method of transform. So now I can define some distributions in continuous case. So let me so let us formally define. I will define only 2 distributions, okay, which is essentially we will need in this course. No need to define all other, okay, just 2, uniform and normal. Okay, that's it. We will be dealing mostly with this, and from discrete we will need binomial, Bernoulli, and so on. Okay, so formally I will define uniform now. So uniform distribution A x continuous random variable has uniform distribution over the interval a b, and it is shown as x tilde u. In my case I will just take u a b. If its PDF is given by so essentially we have used the CDF of uniform in the previous some examples, but here like I am formally defining the uniform. Okay, but although we have used this in examples before. Okay, so let us define this formally. 1 by b minus a less than x less than b, and it's 0 x less than a or x greater than b. So this is a uniform distribution, the most easiest one. Okay, and as an exercise you can find the expectation of x, variance of x. Okay, now let us go to normal distribution. Normal or Gaussian. For mathematicians is Gaussian, for engineers is normal. Gaussian, Gauss is the name of a mathematician, okay, German. So we define it to be, so let's say Z, continuous random variable is standard normal. Okay, it's not that we will define abnormal one later on, but it's just the name is like that. Okay, it's also standard because we have a more generic variant of this. Okay, so first let us see a standard normal variable, a random variable shown as Z. So it's also very trendy to use Z for normal. Okay, usually you will see Z. So Z 0 1, if its PDF PDF is given by, so as you can see previously in the previous example itself we used standard normal, okay, but we didn't define it, but now we are defining it, okay. So the previous example was indeed standard normal, 1 by 2 pi square root e to the minus z square by 2 for all z in R, okay. So this is our standard normal, and this is the most important distribution, okay. It will most important, and it is most important because many of the random variables that we will use, and if the sampling is big enough, that will start approximating like a standard normal. So many of the estimations are eventually done via normal, okay. So we will see how, so that's why it's most important, because for large data problem, okay. What will happen at y equals to 0? So in the previous we had gx, x square is y, right, and we solve for y, right. So we solve for y and then we get plus minus square root of y. So we have two generic solutions here, right, plus square root of y minus square root of y, it gets covered in one of these, right. Why should I separately generic? I have to
But in this it is not defined, right? Y is in the denominator.
yeah, so that's why we exclude that also, right. We exclude that troublesome point. Yeah, we will look into these, and if it's not defined for those value of y, we'll just exclude those in the range. Otherwise we would have taken a closed anyway. Yeah, okay. So whether you remember anything or not, the three things you should remember is binomial, uniform, and standard normal. Most of the generative modeling uses this only, okay. So it's important that we give more importance to normal, and often a normal distribution, because of this exponential term, often a bell curve is synonymous with standard normal, and it's symmetric about 0, okay. So x equals to 0 axis. So this is the so-called bell curve, okay. And it is true that if a data is like big enough, things will evolve like a bell curve, okay. So heights of students, right, at some point the extreme heights will be rare, okay, and most average heights will be like this. So eventually if I take only 2 students, then it's like this, right, or there will be one student like this, right. But I keep increasing the heights, right, I keep increasing the students, then rare events, both extreme side of the rare events are extremely, it's rare, so okay, and average will concentrate, okay. So that's what explains that if the data keeps getting larger and larger, okay, it will kind of approximate the bell curve. You can take any kind of data. The moment you start increasing, it will start becoming like a bell curve, okay. So in fact we can prove that by a central limit theorem. We can prove this result, okay. So even if it's not perfect, so even if the data is like this, but it will approximately be like a bell curve, so we can like estimate via a normal, okay. We can have an approximate solution, okay. So so some of the things that one can prove, except me, like as an exercise I give you right now. So Z normal, then expectation of Z you can prove that it's 0, okay, of standard normal. In fact, expectation and variance are included here itself, okay? But you can separately prove using formula expectation of z is 0 and variance of z is 1. Okay, and we can write the CDF and it is interesting that CDF involves integral, right? And it is interesting that you cannot integrate this. Okay, it's a difficult function to integrate. That's why no one gives you a closed form solution for the CDF. They give you tables. Okay, you read out from the tables. Okay, so that's very interesting because in many other distributions I have CDF explicitly written, but here I will not give you a formula. I just say okay, integrate, but that's the definition, right? Integrate the PDF. That's it. But you cannot solve this because it's e to the minus z square by 2. You cannot integrate. Okay, so that's but tables are given usually. You can look up as a research student. You always have access to the tables. Even during exams, you are given tables, right? So the CDF of standard normal distribution, and it is also denoted by phi. Okay, so z is kind of exclusively reserved for normal, and the phi function is exclusively reserved. Instead of writing fx, capital Fx, I use phi. Okay, so that's also a standard practice to use phi for CDF of standard normal. So phi, so the CDF of standard normal distribution phi is given as follows. So phi x. So by definition, we are supposed. So this is probably a cumulative probability until some x, and this by definition is integral of the PDF of normal. In this case, is f z from minus infinity until x. Okay, we have to cumulate until x. So that's why it becomes. So 1 by square root 2 pi comes out, and then we have minus infinity to x e to the minus. Since x is here, let us change the inner variable to something else. Okay, so let us say u square by 2. Okay, because it will integrate out and eventually it will become function of x because in the limit we have x. Okay, so e to the minus u square by 2 du. Okay, so we use some inner variable u which will eventually integrate. I mean, in this case it won't integrate. We have to do it numerically, but yeah, so just to keep it different from x, which is the limits of the integration, right? So that's it. Like, I'm not going to like say what it is. That's it. So that's where we stop. Okay, and there are like tabular values. Numerical computations could be done for different values. You can approximate this maybe via quadrature rule and so on, the numerical integration techniques, and you can approximate these values, but there is no closed form solution. Okay, so these things are usually calculated via tables. Okay, so no, can't be integrated, can't be integrated to obtain closed form solution. Okay, so you usually need tables, usually need tables to see the values. So these are usually like one can do Google search and find the tabular values for this, and you can say okay, for some x, some value 0.5 or something, you will go to the table and see okay, it's 0.2. It may not be exactly 0.2, it may be 0.25 or something. You can say okay, I will take 0.25 as an approximation of this. Okay, now we go to not so standard normal variable. Okay, so we will not say substandard, but we will just say now normal. Okay, instead of standard normal, this is standard because these guys are fixed as a parameter. It will become a more generic because I will take 0 to be something, 1 to be something. Okay, so I will replace 0 and 1 by parameter. Okay, then it becomes just normal random variable. Okay, so let me use this. So obviously in standard normal I know everything, right? It's not really parameterized, right? The parameters are given. Okay, So I can sample from this because everything's given. If I replace by mu and this, then it becomes a parameterized model. I may do a fitting with this on a given data, find out what is the best mu and variance, and so on, right? Okay, so let us define a normal random variable. Normal random variable is obtained by scaling and shifting the standard normal. Okay, so I will define a transformation which does a scaling of z by some sigma and shifting of that variable by let's say mu, and then it becomes a normal with the obtained one. It becomes normal with mu and sigma. Okay, so that's why standard normal still makes sense, because I can use standard normal and I can do the reverse process. I can unshift and scale it down by sigma. I go back to the standard normal. I use the 5 function values there and come back to find the values in the normal case. Okay, so let us see how we go from normal standard normal to normal, right? So define. So z is exclusively for standard normal, right? So now we can use x, and then we scale the z by standard normal by sigma, and then we shift it by mu. Okay, and sigma we keep it positive. Then now if we compute the expectation of that due to linearity, so this is like sigma expectation of z plus expectation of a constant is a constant itself, right? So it's just a mu, and expectation of z standard normal is 0, so it becomes mu. Okay, so now what we know is that for the transform variable expectation must be mu, and similarly we compute the variance. So variance of x, then it is variance of sigma z plus mu. Now if you recall the variance of formula, right? So variance of ax plus b, okay, it's like a square variance of x. So this is recall. Okay, so that's what it's in that form. So this is like sigma square variance of z, but variance of z was 1, so it's just a sigma square. Okay, so what we know for sure is that for the transform variable the expectation value is supposed to be mu, and the variance of the transform variable is supposed to be sigma square. Okay, so with this we can now define a normal variable which is seen as a transformation of the standard normal. Okay, so definition of normal variable. Okay, so if z is standard normal random variable and x is sigma z plus mu, then x is normal variable is defined to be, okay, defined to be a normal random variable with mean mu and variance sigma square, and in this case we denote x to be normal and mu sigma square. And with the transformation, like we don't necessarily have to use the formula, but given that z was known, we did a transformation. What is the PDF of this, right? So we can do this actual derivation. You can do this as an exercise maybe, okay, or at least see in the notes, the online notes that I'm using. So it is easy to find out the PDF of x, which I'm going to just write down. So PDF, so any distribution is defined by PDF, right? So if someone gives you a distribution, you must ask what is the PDF, right? Without PDF, nothing is defined. Okay, so to find so basically PDF I can write down directly. Okay, so let us write down the PDF. So PDF of x is given by fxx is 1 by sigma square root of 2 pi e to the minus x minus mu whole squared by 2 sigma squared. Okay, so this you can take it as an exercise, as I said. given a variable, you transformed it, and what is the PDF of x? This is the PDF of x, which is defined to be normal in a variable. Okay, the converse is even more interesting. So given a standard normal, sometimes I need to do the calculation, so I need to go back. Okay, so conversely, if x is normal mu sigma squared, then you define and so we know that if x is given to be a normal with mu and sigma square, we know that x must have come from some transformation of the standard normal, right? So we know that x must be of the form like x is of the form sigma z plus mu. So from there I can solve for the z. So this implies z is x minus mu by sigma. Okay, so now if someone wants you to calculate the probability value for the normal, then I want to use the standard normal, right? Because there I have the phi function to calculate, right? So if I am supposed to find, let us say, CDF of the standard normal, so and then this is probability that x less than equal to x, and this is probability that, so this is the same thing as saying that so basically I do sigma z plus mu is sigma z plus mu is less than equal to x, and this I solve for z, right? So this is same thing as saying that probability that z is less than equal to x minus mu by sigma, and this now since this is in z, I can use the phi function, right? So phi of this right now, so this phi of x minus mu by sigma. Now I have the tabular values, right? So I can use the tabular values of phi and estimate CDF at any point x for a normal random variable. So as a very short example on this, this is quite evident, but very short example, like 2-3 lines, because all the work is done by the table itself, right? So we don't have to do much in this case. So example, x follows normal minus 5, 4. So we are given mu to be minus 5. Sigma has to be greater than 0, right? So it's 4 sigma and sigma square, and so find, let us say, find the probability values minus 7 less than x less than minus 3. Okay, so this will be the CDF of x. So this is CDF of x, which is fx minus 3 minus fx minus 7, right? This is how we calculate. And now for CDF calculations for this will now boil down to phi of x minus mu. So x in this case is minus 3, right? So phi of x is minus 3, mu is minus 5, so minus plus 5, so plus 5 divided by sigma is 2. Okay, sigma square is 4, sigma is 2, and minus phi, in this case x is minus 7 plus 5 divided by 2. Okay, so then we can look in the table to get these values. Okay, so we know how to compute probabilities when we have the normal distribution given to us. Okay, so that will be all actually we will need. In fact, everything will go down to normal at some point to do the estimations, right? So that's about continuous distributions. Now let us see, let us do some joint distributions. Okay, so far what we have done is single variable, single random variable, right? Now let us generalize this. So whatever we have learned generalizes more or less, okay, in the same spirit, okay, like what we have done so far. Okay, just the notations are a little bit more now, but when we have more random variables, there is a concept of joint also. Okay, so So joint events happening, right? A intersection B in this case is like X and Y happening, right? So the events A and B are denoted by X equals to X, Y equals to Y, and so on, right? So now we can talk about the joint probability functions, okay? So I can define the joint PMF So now essentially we are going to two random variable, okay? So now we are moving to two random variables, and at some point we will generalize this to vector of random variable. Okay, so let us say two random variable. So in the discrete case, that's why we use PMF. This is discrete. The joint PMF of two discrete random variables x and y is defined as pxy. So these are the notations that we use, xy, which is probability that x equals to x and y equals to y. Okay, so this is the same as saying probability that x equals to x and y equal to y, and this is the same as saying that probability that x equals to x is an event, right? Intersection y equals to y. Okay, so these are all same difference. So basically we are asking for intersection of two events. Okay, that's what joint means. So some of the properties that we have is the joint also, if I sum over all the joint values xi comma yj, then xi yj in Rxy, it must sum to 1. Okay, this is over all possible range of x and y. If I sum these joint probability value, it must be 1, because then only we will say it's a valid PMF also. Okay, so since we have a joint, we can talk about marginal also. Okay, so from joint we can obtain marginal by summing over one of them. So if I want over x, then I sum y. If I want y, then I sum over x. So we can define a marginal PMF. So marginal PMF of x and y. So in this case, Pxx is sum. So if I want marginal with respect to x, then I will sum over y. Okay, so this is yj in Ry, Pxy xi yj. Okay, for any x in Rx. So if you want marginal with x, you sum over y. If you want marginal with y, you sum over x. Okay, so if you want marginal with y, then you sum over x. Okay, so these are formulas to obtain marginal. Then similarly, we can define something called joint cumulative distribution function. Okay, so joint cumulative distribution function, and this is defined as fxy xy, and this is probability that x less than equal to x, y less than equal to y. And if I have a joint, then I can also get the marginal CDF. So then in this case, I will again sum over infinity for one of them, right? So if I want marginal with x, then I will write this as fxy and then x infinity, which is defined as limit y tends to infinity f xy xy. And similarly, I can define marginal with respect to y, and this will be f xy infinity y, and this is limit x tends to infinity f xy xy. Okay, so as you can see, for the marginal, I sum over the x if I want y. If I want y, then if I want x, then I sum over y. If I want y, then sum over x. Okay. So in this case, you can see x and y values like this. It's a discrete probability, right? And you are summing over the x one dimensions, right? Okay, now let us see how we can condition. Okay, so to condition we needed two random variable, and this is indeed the setup where we have now two random variables coming in picture. Now we can talk about conditional probability. Okay, so what you can recall is probability of A given B is probability of A intersection B by probability of B. So this is something you recall. Obviously probability of B should be greater than 0. Okay, so in the same spirit we can define conditional PMF and so on. Okay, so for instance probability that probability x given A xi is probability that x equals to xi given A is probability that x equals to xi and A. So in this case I've extended this to the two sets. Okay, but the point here is that I can extend this to A. I replace A by y also. Okay, I'm just going step by step. So the first I remember A given B, then I say okay x given some set A, but then I can replace x by even some random variable also. So let us do that. So in general, so for discrete random variables, so let us say for discrete random variables x, y, the conditional PMF of x and y are defined as probability x given y x I y j, and this is p x y x I y j divided by p y y j. So just to like connect things, we have written these two steps, but this is what we actually wanted. Given a conditional probability of random variable x given y, and this is, so you can see this as events, right? So A, what is the counterpart of A? A is x, capital X equals to xi is an event A, capital Y equal to yj is an event B, okay, divided by probability of B. So y equals to yj is the event B, right? So it's just a notation, right? We already know this. Okay, so now with this we can also define independent random variables, right? So independent random variables, so two events were independent if the joint was product. So probability of A intersection B is probability of A times probability of B. The same thing will be extended here. So the x and y will be independent if probability of joint will be product of the marginal, right? So we can define independent so independent random variables, so x, y independent if the joint is product of the marginal. Okay, for all x and y obviously. And obviously like previously we have said that in the independent case probability of A given B is just probability of A, right? Because the BB gets cancelled, right? So same thing can be written here also. So if they are independent, then yj xi is we can write this in terms of the CDF also. So so this is using the PMF, and equivalently, so equivalently first let me write down in terms of CDF. So CDF also splits. Okay, so CDF also becomes product of the marginal CDFs. Okay, this is true for all x and y. Okay, so then we can define conditional expectation. Okay, so conditional expectation we can define as if we, so x given some event A, then this will be xi probability of x given A xi. Okay, so we can define conditional expectation like this. The only thing to note is that here we have a conditional PMF. If you want conditional x given a, then you should put the PMF of x given a and evaluate on the xi's. Okay, so that's the only thing you have to keep in mind here. Okay, so essentially you see x given a as a random variable in itself, which has some PMF function defined. Okay, so you can see this as some function here, and for which you have the PF, so you can compute the expectation of that. Okay, so then we can also do the same thing by using the random variable notation. So y equal yj is sum of xi p of x given y and then xi yj. Okay, and xi in the range of x, right? Here I did this for an event, and here I'm saying it for a random variable. Okay, so y equal yj is some event a, right? So it's just notation here. Okay, so now we know what is conditional expectation, and we can write down law of total probability, law of total expectation. So law of total probability. So we have done a little bit of this. Essentially the idea here is to find a partition of the sample space and use that partition to compute the probability values, right? So probability that x, so we can say that it's partitioned by y. Okay, so probability that x is in a, I can use the partition given by the y random variable. So probability that x is in a given y equals to yj, okay, and yj in ry for any set a. Okay, so this is law of total probability, and obviously I'm missing something here. At the end I should have p y yj also. P y yj. Okay, this is law of total probability, and similarly we have law of total expectation of total expectation. So you see law of total expectation, then let b1 b2. So we always need partitions when we use a law of total things, right? Is a partition of sample space S, then expectation of x will be sum of expectation of x given bi and probability of bi, I sum over these partitions, right? And I can extend this again, because in place of bi's I can have yi's as a partition. So I can just substitute b by y equals to yj. So for random variables x and y, we can write law of total expectation as sum of expectation of x given y equals to yj and probability of y yj and yj in ry, range of y. So we are recalling some definitions from probability and so on. So let's see, like just one more class of probability.